So now that we are experts in taking a function f of t and turning it into a Laplace transform, so we're taking it into Laplace world, and we are experts at taking something that lives in the Laplace world and coming out of Laplace world by applying that inverse Laplace transform. Now we can start talking about derivatives and taking the derivative, the transform of a derivative. So that's what theorem 722 is going to do for us. So if we have a function f prime, it could be f double prime, all the way up to the n minus first derivative. These have to be continuous from 0 to infinity. They have to be of exponential order. And this derivative has to be a piecewise continuous function on 0 to infinity. Then we can take the Laplace of that. So let's we're going to talk about first and second order derivatives primarily. Let's apply that definition to figure out what the Laplace of all of these are going to look like. So if we want to take the Laplace of y, it's just going to be y of s. So there's my s there. I'm going to use cursive s's. If we want to take the Laplace of y prime using this definition, and I'm going to recopy that down below so I have more room to write. So here's our theorem recopied. We said the Laplace of y is some function y of s. When you're writing things, be very careful with your s's and your 5's. It's really easy for me to get my s's and 5's mixed up if I use a regular s and 5. So just be careful on those. Now let's take the Laplace transform of y prime. So the n's going to be a 1 there because this is going to be the first derivative. So we're going to have s to the first times our function. I'm going to call it y of s minus, and then we're going to have s of 0, f of 0. So I'm going to simplify that just a little bit. That's s y of s minus f of 0. So notice you've got to have f of 0 to apply this. Let's look at the second derivative. We're applying this definition. Now our n is 2. So this is going to be 2 minus 1, which is 1. And then this is going to be s to the 0, f prime of 0. So you've got to stop when you get to n minus 1, which will be 0. So you can't go below s to the 0 power. And then let's do, just for fun, a third derivative. Substituting everything in we know. This is going to be s cubed, y of s. I'm going to rewrite these f of s's up here as y of s as well, just to be consistent. Because I'm going to use y of s throughout the rest of the Laplace stuff. And then s to the n minus 1. In this case, it would be s squared, f of 0. Then we're going to have s to the first, f prime of 0. So the next one, applying this information, would be f to the double prime of 0. It would be times s of 0 here. So you can see how this says it's going to be f to the n minus 1. That's a derivative. Remember that notation, the parentheses, and the exponent says that that's a derivative. So we should have, since we're starting with the third derivative, we should end up with f of the second derivative of 0 right there. So we've got to have some conditions to be able to apply this. Now, these are things you may want to write down on your cheat sheet. This guy's kind of important. That one's important. Just using that simplified. That one's important. And then that one's important. Using those simplified versions of those. That's how we're going to solve differential equations, because we're going to take that differential equation, we're going to take it to Laplace, we're going to solve it in Laplace world, which is going to be much easier for us, and then we're going to take that inverse to turn it back into something in terms of t. So just to kind of see the path we're going to travel here. We have a Laplace transform of a linear differential equation. We have to have constant coefficients for this method to work. So we're going to start with some kind of differential equation that's written in terms of t. We're going to apply the Laplace transform. So now we have something that lives in the Laplace world, and we have everything in terms of s's instead of the t's that we started with over here in the rectangular world. And then we're going to solve that equation for y of s. That's just going to be some algebra techniques for us to solve. Then we're going to go back to rectangular world by applying the inverse Laplace. And then we're going to have the solution to our equation. Piece of cake, right? 4 simple steps. So let's look at a few examples. Let's say we have this guy. This is a first order differential equation. And keep in mind, we could solve this using other techniques, but I want to do this using Laplace transforms. So what we need to do is we need to start by taking the Laplace of each side. So if I take the Laplace, this is y prime. I have to take the Laplace of both sides of the equation, and then using those properties of linear transformations, we can rewrite it this way by taking the Laplace of each piece. I did pull those constants out, so we're good to go there. So I'm just going to kind of write this out. When we take the Laplace of y prime, we derive that on the last page using that formula. There's our Laplace of y prime. It's going to be s minus y of s, sorry, s times y of s minus f of 0. Now, in this case, y of 0 is 6. So now let me take the Laplace of y. Now looking at this piece, we found this guy. So the Laplace of y is just this function y of s. And then if we take the Laplace of sine of 2t, going back to our formula chart, the sine of kt using 7 is going to be 2 over s squared plus 2 squared. Which is 2 over s squared plus 4. So let's make our substitution. We have all the pieces. We've taken the Laplace of every single piece. So the Laplace of y prime is s y of s minus 6. The Laplace of y was y of s. And the Laplace of sine of 2t is 2 over s squared plus 4. So simplifying. Now let's solve this guy for y of s. I'm going to move that 6 over. Now, I'm going to get a common denominator over here. So I'm going to continue working with that right-hand side, and I'm going to change color so you can see that. So we're going to have 26 plus 6 times s squared plus 4. All over that denominator, s squared plus 4. So that's going to give us 6s squared. This is going to be 26 plus 24, which is 50, over s squared plus 4. Now let's go back to the left. Notice we could factor a y of s out here. And if we do, we're going to be left with s plus 3. And that's going to be equal to 6s squared plus 50 over s squared plus 4. So then now we have y of s. Solving for y of s. That's going to be your goal in all of these. And then once you do that, you're halfway there. So check that out. This was really easy for us to solve for y of s once we took this and we applied Laplace transformations. So we've got to solve this because now we have to take this out of Laplace transforms, out of Laplace world, and we've got to go back to the real world, our regular world, our rectangular world. But to take the Laplace transform, we need to do some tweaking here, and that's going to require partial fractions. So we have a linear term. I'm going to rearrange that denominator, and then we have an irreducible quadratic. So applying the partial fractions, we have the numerator 6s squared plus 50 is equal to a times s squared plus 4 plus bx plus c times s plus 3. I'm going to change that to a bs there, just to be consistent. We're so used to dealing with x's, it's hard to make that transition sometimes. So we have as squared plus a times 4 plus bs squared plus 3bs plus cs plus 3c. So now we're going to compare coefficients on the left and on the right. If I look at s squared, I have a 6 on the left, a plus b on the right. S, I have 0 on the left. I have a 3b plus c on the right. And then constants. I have a 50 on the left. I have a 4a plus 3c on the right. If we take all of this, plug it into a matrix, and then do RREF, you will always get a unique solution. And I got 8, -2, and 6. So that tells me that y of s can be rewritten as 8 over s plus 3 plus -2s plus 6 over s squared plus 4. So since we need to apply the inverse Laplace, I need to split the numerator for that second fraction here. So it's going to be a minus 2s over s squared plus 4 plus 6 over s squared plus 4. So now let's apply the inverse Laplace. When I take the inverse Laplace of y of s, we're just going to get y of t. We could also call it f of t. Looking at 1 over s plus 3, we're going back to that Laplace worksheet here, that table. And that's going to be number 11. We've just got to figure out what a is. And in this case, we could rewrite that denominator as s minus negative 3. So then a is going to be equal to a negative 3. So this ends up being e to the negative 3t. Minus 2, this guy, going back to here. We had s over s squared plus a number squared. That's number 8. So that's your cosine. And the number we have to square there is 2. Our k value is 2. And then here, going back, it looks really close to number 7. We just have to make a tweak here. Think about what we're missing in that numerator. We're missing a 2 because our k is 2. And we can multiply that in as long as we compensate with a 1/2 somewhere else in the problem. So that number in front ends up being 3. So there's our final solution. So you can see how much fun these are. I actually like these. These are one of my favorite things to do in this class, is using Laplace transforms. So that's solving a first order differential equation.